Kia ora, and today we're just going to go through a past exam for this course. So we're not going to do every question, but we're just going to do questions that are related to Test 3, because of course this year Test 3 is only going to be on, or the exam is Test 3, is only going to be on Units 5 and 6 of our course. Okay, so we're only going to look at classifying critical points of linear and nonlinear systems, and numerical methods. So that gives us 3 questions. Question 9 is a linear systems question. Question 10 is off the screen. Question 10 is a nonlinear systems question, you can see here. And question 11 is a numerical methods question. Here we're asked to use the improved Euler's method to solve this first order ODE. Okay, of course in Test 3, your Test 3, you'll have more than 3 questions, but they will only be on these topics: linear systems, nonlinear systems, numerical methods, Units 5 and 6. So let's get into it. So starting with question 9 here, we have this linear system, and we have this constant sigma. Okay, and sigma is an unknown at the moment. Okay, so we're asked to investigate the type and stability of critical point for sigma greater than 0 and sigma less than -1. So of course, well, the first thing we should say is that it's a linear system, so 0, 0 is the critical point. Okay, so 0, 0 is the critical point. Let's then write this in matrix form. So x prime is equal to a times x, where x is equal to xy. My matrix A is 2 times x, so 2, 1 times y, sigma times x, and then 0. Okay, so let's calculate the trace of A. Okay, well the trace of A is 2 plus 0, which is 2, and we were calling that tau. Determinant of A is 2 times 0, which is 0, minus sigma times 1. So minus, determinant of A is minus sigma. Okay, and we were calling this delta here. So the eigenvalues of matrix A, if you recall for this 2 by 2 system, is tau plus or minus the square root of tau squared minus 4 times delta all over 2. Okay, well let's put the numbers in there. Tau is 2, so 2 plus or minus 4 delta. Well, sorry, delta was negative sigma, so this should be plus 4 sigma all over 2. And of course we can simplify that. 2 divided by 2 is 1. Square root of 4 is 2, so we could bring that we can bring this 2 in the denominator inside the square root, so square root of 1 plus sigma. Okay, so our eigenvalues are 1 plus or minus the square root of 1 plus sigma. So for sigma greater than 0, well, this square root here is going to be positive. So 1 plus sigma, if sigma is greater than 0, is going to be positive. So we're going to get real solutions. And not only that, but sigma greater than 0, 1 plus sigma, the square root of 1 plus sigma is greater than 1. So we're actually going to get real eigenvalues of opposite sign. Opposite sign. So we're obviously going to have an unstable saddle here. But if you didn't know that if we have real eigenvalues of opposite sign, if you didn't know that means that we've got an unstable saddle point, you could check your table of useful information, and I definitely recommend you have that next to you when you are taking this test 3. Print it out, have it right in front of you. It will be provided with test 3, but it's better to have a printed copy if you can. Okay, what about sigma less than -1. Okay, well, 1 plus sigma then is 1 plus sigma for sigma less than 1 is, so we get the square root of something negative something. So we get complex conjugate eigenvalues. Okay, not only that, but we get complex conjugate eigenvalues with positive real part. So with positive real part. Okay, so, well, again, you can refer to your table of useful information, but if I have complex conjugate eigenvalues, I have a spiral. But if I have positive real part, I have an unstable spiral. So I have an unstable spiral point at 0, 0. Okay, so we've answered question A now. Okay, good. But now we're asked to sketch the phase portrait of the system for sigma equals -2. Well, if sigma equals -2, then we have this case, right? We have this case here, because sigma less than -1 gave us an unstable spiral point. So we have an unstable spiral point. So I'm just going to draw a spiral emanating out of the origin, and it's unstable, so we're pointing away. As we travel along this curve, we're moving further away from the origin. So we'll accept something like that. Okay, so again, you need to be able to classify systems of critical points of systems of linear equations. So again, make sure you refer to your table of useful information and have that printed out in front of you when you're solving these problems. Okay, but now moving on to question 10, the nonlinear systems case. Well, we're given here that one of the critical points is 0, 0. Well, that's obvious. If you look at the equations, there's an x and a y and everything. So 0, 0 is always going to be a critical point in this case. But we're asked to find the other critical point. So we're kind of given a clue here, the way they've worded the question, that there is only one other critical point. Okay, so, well, we know if we write down two equations here, we know that 2x minus y plus xy equals 0, and x minus 2y minus xy equals 0. These have got to be true simultaneously for this for a point to be a critical point. So what I'm going to do is I'm just going to add these together, because I can see if I do that, these two terms here are going to cancel. There's going to be a positive xy and a negative xy. So if I add these two together, I get 2x plus x is 3x. Minus y minus 2y is minus 3y. The xy plus xy and minus xy add to 0. And the right-hand side adds to 0. So we get basically x is equal to y in this point. So we get x is equal to y. So now what I'm going to do is in equation 2, wherever I see an x, or actually, let's say whenever I see a y, I'm just going to replace it with x. Okay, so I've got an x minus 2y, but now I'm just going to write that as 2x minus x times y, which I'm just going to write as x squared equals 0. Okay, so, or in other words, x times x plus 1 equals 0. Okay. So there are two solutions to this this equation here, of course. X equals 0, which would imply that y equals 0, but we already have that critical point, so let's not worry about this. And x equals -1. So this is the one we're going to worry about. So x equals -1 implies that y equals -1 as well. So -1 is a critical point. Great. So now that we've done that, we have to determine the nature and stability of these critical points. So what I need to do is calculate the Jacobian of our system. Okay. So if I look at my first equation here, and I take the derivative, the partial derivative of that equation with respect to x, I get 2 plus y. Okay, if I take the derivative of the same equation with respect to y, I get -1 plus x. Okay, now if I look at the second equation here, if I take the derivative of that equation with respect to x, I get 1 minus y. And if I take the derivative with respect to y, I get -2 minus x. Okay, now I need to evaluate this Jacobian at the two critical points. So A, I'm going to start with 0, 0, because that seems like an easy one. So if I substitute x equals 0 and y equals 0 in there, I'm going to get 2, -1, 1, -2. And actually, let's just do the other critical point while we're here. -1, -1. I get 2 plus -1 is 1. Oops, 1. -1 plus -1 is -2. 1 minus -1 is 2. And -2 minus -1 is -2. Okay, great. So now what we need to do for both of these equations here, representing the Jacobian evaluated at the two critical points, is find the eigenvalues of these. Okay. So for this, on the left here, the critical point 0, 0, I'm going to write tau, my trace, is just equal to 2 plus -2 is 0, in fact. Okay. So, well, let's calculate the determinant of A. Okay, well, that's 2 times -2, which is -4, minus 1 times -1, which is positive. So we get -4 plus 1 is -3. So while tau is 0 here, so this is fun. So what do I going to get? My lambda1, lambda2 is equal to tau plus or minus, so 0 plus or minus the square root of 0 squared, which is 0. So 0 minus 4 times -3, all over 2, which of course is, what is it going to be? 0 minus 12, so I get 0 minus -12, so I get the square root of 12 over 3, plus or minus the square root of 12 over 3. Okay, so I get real eigenvalues of opposite sign. So I'm going to get, if I check my table of useful information, or if I just remember, it's going to be unstable saddle point. Okay, so 0, 0 is an unstable saddle point. Okay, well, what about this second one here? Well, again, I'm just going to calculate the trace of A. Again, that's 0. 1 plus -1 is 0. Delta is the determinant of A. Okay, so here I'm going to get 1 times -1, -1, minus 2 times -2, which is positive 4, right? So in fact, here I'm actually going to get -1 plus 4, so 3. So I can already see here that I'm going to have complex conjugate eigenvalues, but just to show you, lambda1, 2 is the trace, so 0 plus or minus 0 squared minus 4 times 3 over 2. Okay, so here I can already see that this is going to be plus or minus I times square root of 12 over 2. So here I've got complex conjugate eigenvalues. So complex conjugate eigenvalues with 0 real part. Okay. So, well, actually, let's go and check our table of useful information for this one. Because, okay. So the stability of nonlinear systems, it's come down to this pure imaginary point here. So the stability of this pure imaginary eigenvalues here is indeterminate, and we have a center or a spiral point. So we have either where are we? So this point, -1, -1, or was it -1, -1? Yep. -1, -1 is either a center or spiral point of unknown stability. Okay. So again, in your test 3, you're going to have to do this probably multiple times. You're going to have to classify nonlinear systems, the critical points of nonlinear systems. Okay, and the other thing, of course, that's going to be in test 3 is going to be numerical methods. So here we're going to solve something, some basic, simple first-order ODE using the improved Euler method. Of course, we're not using MATLAB for test 3, so everything's going to be by hand, so it should be relatively straightforward, 1 or 2 steps. But you do need to know how to solve using the improved or the Euler's method, standard Euler's method, and also RK4 as well. Okay, so let's do this. Okay, so let's get to it. I have pasted the improved Euler's method here down below. So we've got a, if you recall, this is a predictor-corrector algorithm. And we have to do 2 steps for the improved Euler's method. So for part A here, we're asked to approximate y when x is equal to 0.2 using 1 step of the improved Euler's method. So because I'm only using 1 step, and I'm starting, my initial condition is when x equals 0, y equals 1, I'm moving in 1 step from 0 to 0.2. So I know that my h, my step size, is 0.2. Okay, I know that my y naught is equal to 1 by the initial condition here. And I know that my x naught is equal to 0, again by the initial condition given here. Okay, so I have my y naught, my x naught, and my h, so I can start to apply this method now. So this is part A. So y1 star is equal to y0 plus h times the function f evaluated at x0, y0. So what is my function f? Well, f of x, y is just the right-hand side of the ODE. So in this case, it's just 3y. Okay. So if we chuck in these numbers here, y1 star is equal to y naught, which is 1, plus h, which is 0.2, times f evaluated at x naught, y naught. Well, f is 3y, and y naught is 1, so this is just 3. Okay. So this is, of course, it's just equal to 1.1 plus 0.6, so 1.6. Okay. And so, in fact, that is the value you would get if you were using the Euler's method, in fact. But that's just our predictor for our improved Euler's method. So now we should write down y1 is equal to y naught plus h times the function evaluated at x0, y0, plus the function evaluated at x1, y1 star over 2. Okay, so that's the formula for Euler's method. Again, we'll check in the numbers. Well, y naught was 1, h was 0.2. The function f is 3y, so evaluate that at x naught equals 0, y naught equals 1. We get 3 plus 3 times 1.6, because our y1 star was 1.6. So 3 times 1.6 over 2. Okay, and basically you just want to put that into your calculator, and if you do that, you should find that this is 1.78. So in other words, y1 is 1.78. So that's our approximation. That's our approximation of the exact solution, 0.2. Okay. So we asked here now to find a bound for the local truncation error in Y1. So of course, we're going to have some local truncation error here. So let's just go back to our table of useful information for a second. Okay, and well, our numerical methods are given on the last page of the useful information. So again, make sure you have that when you take test 3. And the local truncation error of the improved Euler's method is the error is less than 1/6 M3 times H cubed. H is the step size, and M3 is the maximum value of the third derivative on the domain. Well, it's going to be x0 to x1. Okay, the maximum of the third derivative of the exact solution, I should say. Okay, but we're given the exact solution, right, in this problem. Exact solution is y is equal to e to the 3x. So for part B here, y is equal to e to the 3x. So I can take 3 derivatives of this thing, right? I can take 3 derivatives, so y prime, y double prime, 9e to the 3x, y triple prime, it's 9 times 3, it's 27. Okay, so here's my third derivative, right? And I said that the local truncation error is less than or equal to 1/6 times the maximum of this third derivative here times h cubed, or h squared? H cubed it should be. Okay, great. So M3 equals the maximum on x0, which was 0, to 0.2 of 27 e to the 3x, okay? Well, this is going to be maximum because the exponential is monotonically increasing. This is going to be maximum when, so this is going to be max when x equals 0.2, okay? So if I plug in the numbers here, well, this is when M3, when x equals 0.2, is roughly 49.2. So the error is going to be less than or equal to 1/6 times 49.2 times 0.2 cubed. Okay, well, again, I don't know how to do that in my head, so please use a calculator. Please bring a calculator to test 3. But when I put that in my calculator, I get the truncation error is less than or equal to 0.0656. Okay, so my solution was 1.78, and the error in that is less than or equal to 0.06. So, relatively small error for that step size. Okay, what part C is asking us directly, compare the error in Y1 with your error band. So Y1 was equal to 1.78. Let's calculate the exact solution. Okay, because remember that y of x, the exact solution was e to the 3x. So the exact solution when x equals 0.2 is the exponential of 3 times 0.2. Again, I don't know that in my head, so bring a calculator. And it turns out that that is 1.8221. So our error, our real error, is equal to 1.8221, the exact solution, minus our prediction of it, 1.78. So we predicted that y was 1.78 when x is 0.2. If I again put that in my calculator, that's 0.0421. Now this is less than the truncation, the maximum truncation error. Right? So this number here, yeah. So we could say that, yeah, our error is less than the theoretical one. Okay. So that is the last 3 questions of the 2017 exam done. I highly recommend you go through multiple previous exams. So look on the library for those, and there will be some on the stream site. and just work through those. You may not have solutions to all of them, but it gives you a taste of what you might be expecting. And if you do have any questions, please get in touch. Okay, thank you.